Hello, this is lecture number 4 for Monday of third week. And we're shifting from polymers now to metals. We'll spend a lot of time on metals. And so we'll start that at the nanoscopic and microscopic level, talking about the difference in structures in different metals that contributes to the properties and how those can be manipulated. And we'll focus on the two main crystal structures in metals, the body-centered and face-centered cubic structures. And we'll talk about, for each of those, how many atoms are in a unit cell, the atomic radius ratio to the size of a cell, planes and directions. This will all make a lot more sense once I get to it. And then how to calculate the theoretical density. So the first crystal structure that we'll talk about is the body-centered cubic. So the image here on the left, let's see, there we go. Here is a simple cubic structure. There aren't very many materials that have that structure, but you can see why it would be called that. The body-centered cubic structure then is cubic, and then there's an additional atom at the very center of this cube. A single set here, the cube with the atom at the center as well, is called a unit cell. And the crystal then is a bunch of unit cells in 3D space. So let's see here. A few things to note. We're going to be calculating density in a bit, and that density would be a function of the mass, and the mass would be a function of how many atoms there are in one of these cells. And so for the body-centered cubic unit cell, there's one central atom, and then there's an atom at each of 8 corners. But the whole atom isn't in the cell. Only part of that atom is in the cell. It's actually 1/8 of the atom. If we think just about this atom right here, it is in the cell that's shown, the cell below it, the cell in front of it, and the cell below that, the cell to the left of it, and the cell below it, and the cell in the front, and the cell below that. This is in 8 different cells. So there's 8 corner atoms, but only 1/8 of each is actually in that cube. And so the total number of atoms, whole atoms per unit cell, is 2 for body-centered cubic. For any unit cell, the length of any side, since it's cubic, it would be any side. The length is given a symbol lowercase a, and that's called the lattice parameter. All right. So we look at this next slide. We need to know, if we're going to calculate density, we need to know how much one unit cell weighs, and we can get that from the number of atoms. We also need to know how large one unit cell is. We typically will know the atomic radius, and so we could use the atomic radius to get this size, because this image here of the BCC unit cell is actually what we might call an exploded view. The atoms are actually in contact. And if I were to just look at this plane and draw it in reality, I have that center atom And then I have four corners. And let's see if I can get a better. So that's what the cell actually looks like, the atoms. And so let's try this, see if I can do a better job, maybe by that might make it better. There we go. So that's what this this plane looks like. And like I said earlier, the length of any side of this is A, that lattice parameter, and the volume then would be A cubed. And if I look just at this plane that's cutting across there, this is defined by the fact that these atoms across this diagonal are in contact. And so let's try a different color here. And so if this dimension is A, then this dimension is the square root of 2A. Here's A, and this is square root of 2A. And if that's true, then the dimension from the center of this corner across the middle center atom to the center of the opposite corner, that length would be root 3A. Okay, so these atoms are in contact along this diagonal. We call this the body diagonal because it's going completely across the unit cell, top to bottom, right to left, back to front. That dimension is square root of 3 times A. And so for this crystal structure, for BCC, 4 radii, there's 1, then 2, and then 1 more. 4 atomic radii is equal to the square root of 3 times the length of the side of the unit cell. And this is true, this is a defining characteristic of BCC. Sometimes we need to convert from A to R or from R to A, so we could write this equation as R being equal to the square root of 3 times A over 4, and that's A being equal to 4R over the square root of 3. It's just different ways of writing the same equation. Okay, and I gave myself an extra slide to make these calculations, so we can just skip the next slide. We don't need that now. And I know this is messy, and I apologize for that, but I want to try and illustrate something. So what I've done here is I've taken this, let's see, I want a color other than red or blue. So here, this is one BCC unit cell. Okay. And I've just duplicated that in 3D space. All right. And then once I did that, I went from diagonally from one corner to the corner on the same face that's opposite to the corner down here. So I'm drawing a line that's going across here and defining that's a defined direction. And I could pick the line that goes across the front and back faces and the line that goes across the top and bottom faces. Those are the three directions where deformation occurs in BCC. And you can see that those three directions created a plane, and that I've got a plane above it. So there's two planes here, darker purple and lighter purple. And those are the planes that would slide past one another during deformation. So deformation occurs when certain planes slide past one another in certain directions. All right. So we need to do a little bit of crystallography, I guess might be the best word for it. In 3D space, there's a convention for identifying or labeling or describing directions and planes. So we aren't going to go into depth with that, but a direction that goes from along an edge, like that, or that, or that, is of the type 1, 0, 0. We get that direction, we come up with that by noting from the beginning to the end how many lattice parameters or how many units a direction moves in X, Y, and Z. So this direction that's moving up is not moving in the X direction. The X direction is this. It's not moving in the Y direction. Positive Y is that. But it is moving 1 unit in the Z direction. That's positive Z. So that direction, and we use square brackets to indicate a direction, that direction is 0, 0, 1. And the direction here is this is the 1, 0, 0 direction. And the direction that's coming out from the board or out from my screen is moving 0 in X, 1 in Y, 0 in Z. And you know what? That's Y, and that's X, and that's Z. Okay, now we're not going to spend any more time talking about those edge directions. They're not important in talking about deformation. But the directions that would be diagonals across a face, those are important. So if I have a direction that goes, say, from here to there, and that's X, and that's Y, and that's Z, then this direction is moving not at all in the X. It's moving plus 1 in the y, and plus 1 in the z. So that direction is the 0, 1, 1. 0 in x, 1 in y, 1 in z. The direction that's perpendicular to it will be, in this case, moving 0 in x, plus 1 in y, minus 1 in z. So this direction is 0, 1, 1 bar. A bar is used to indicate a negative direction. Now there's an identity that says that the direction A, B, C is perpendicular to the direction X, Y, Z. Those are all digits. If A times X plus B times Y plus C times Z equals 0. So I can see that these are perpendicular directions. A times X would be 0 times 0. B times Y would be 1 times 1. And C times Z would be 1 times negative 1. And that does sum up to 0. So there's two directions, perpendicular directions on this front face. And those same two directions are on the back face as well of that cube. We also have a top and bottom, which would have two directions, and a left and right face, which would have two unique directions. So what do those look like? Let's talk about the ones on the top and bottom. So here's one, and here's the other. And it doesn't matter which end we put the point of the arrow on, and I'll show you why in a sec. So this direction is moving -1 in x, +1 in y, and not at all in z. So this is 1 bar, 1, 0. This direction that's perpendicular to it is also moving -1 in x, but it's moving -1 in y as well. So this direction is 1 bar, 1 bar, 0. And again, a times x, so -1 times -1, that's +1. Plus -1 times 1 is -1. Plus 0 times 0, that is equal to 0. So those are the directions that are perpendicular on the top and the bottom face. Notice that we're not moving in the z direction here. So the top and bottom face, which are 1 unit apart by z, have zeros for the z indice. Front and back have zeros for the x index. So that means that the left and the right faces will have a 0 at the y index. So let's see, we've done the top and bottom, front and back. So, okay, so let's look at this direction. And this direction. So this first is going -1 in x. It's not moving in y, +1 in z. So 1 bar, 0, 1. And this perpendicular direction is going from here to here, -1 in x, not at all in y, and -1 in z. So this would be 1 bar, 0, 1 bar. Now, just to show you that it doesn't matter which direction I've drawn this. If I, instead of having the arrow down, if I had the direction, this direction is moving this way, it's still perpendicular. It's moving +1 in x and +1 in z. 1, 0, 1. And that, with that dot product, or that multiplying each index, ax plus by plus cz, for those two, would be 1 plus -1 plus 0 times 0 plus 1 times 1. It would also be 0. Okay? So there's 6 of those directions. There's 2 that have 0 at the x, 0, 1, 1, and 0, 1 bar 1, or 0, 1, 1 bar. And this could be or 0, 1 bar, 1 bar. Those are parallel. That's just the arrow pointing in one direction or another. So I could have these two, 0, 1, 1 and 0, 1 bar 1, or I could substitute either for one of them, as long as it's the exact negative. So 0, 1 bar 1 bar is the exact negative of 0, 1, 1. 0, 1 bar 1 is the exact negative of 0, 1, 1 bar. So I've got those two, and those I have 0 at x, so that means that those two directions are on the front and back face, because they're not moving in x. And then the other 4, I could put 1, 0, 1, and 1 bar, 0, 1, or 1, 0, 1 bar, but not both. And then 1, 1, 0, and 1 bar, 1, 0. So those are the 6 directions in the family. And a family of directions, we use this kind of bracket in the family 1, 1, 0. In the family 1, 0, 0, there are 3 members. But again, that isn't a very important set of those directions aren't important in metallurgy. Okay, now I really want to have another blank slide. I am going to pause here and add a slide. See if I can do that. Okay, I got a spare, a new empty slide to work with here. So let's see. We have discussed the family of directions 1, 0, 0 and the family of directions 1, 1, 0. So let's talk about the family of directions 1, 1, 1. The 1, 1, 1 direction family are directions that go from one corner to the very opposite corner of the cube. So for example, if I take the direction that goes from the back, bottom, left corner all the way up to the top right front corner. It's going to move +1 in X, +1 in Y, and +1 in Z. So that direction is the 1, 1, 1 direction. And there are 4 of those type directions in a cube. If you think about a direction that starts in the back left corner, like the one I've drawn, then there would be one that would start in the back right corner. There would be a different one in the front right corner, bottom, and a different that starts in the front bottom left corner. So if it started in the front right bottom corner and went that way, it would be going -1 in X, -1 in Y, and +1 in Z. So that direction would be 1 bar, 1 bar, 1. So the members of that family, 1, 1, 1, are the direction 1, 1, 1. The direction, I'm going to make the first one negative, the other two positive. I'm going to make the Y index negative, the other two positive, and I'm going to make the Z negative, the other two positive. Those are the 4 directions. The one I got here was the 1 bar 1 bar 1, which is the same as the 1 bar 1 1. It's just the complete opposite of one another, which means that they're the same. So I've got 3 different families of directions. The family of edge directions, oops. Those are the family 1, 0, 0. The family of face diagonals. And there's 6 in that family. They go across faces. And that's the family 1, 1, 0. And then lastly, there's the family 1, 1, 1 that I've drawn here. So for BCC materials, they deform permanently in the I should say family. They deform permanently in the one, one, one family. Just like these 2 that I'm seeing here. And they deform along that plane that's defined by those 2 directions. So deformation in BCC metals, okay, there we go, happens on planes like this one, in directions like that. So I'm going to, in class, when I do the lecture, I'm going to go use the dry erase board to maybe illustrate this more clearly, but this plane is the one, let's see, the 1, 1 bar 0 plane, and that's the family of planes that are slide past one another in permanent deformation of BCC. Like I said, I'll use the dry erase board tomorrow to really illustrate that, and you can see all of the different families. I can't fit it all on one page here and without making it extremely confusing. So I'll talk about that in class. All right, so BCC, atom at the center, atom at each of the 8 corners. There's 2 atoms in a unit cell, and 4R is equal to square root of 3 times A. The other crystal structure is a face-centered cubic. And this looks very confusing, but I think if you just hang with me, it will be clearer. I tried to just use this as a way of showing where the atoms are. So you start with a cube, an atom at every corner. And then there's an atom at the center of every face. So here's the atom that's at the center of the back. And then here's an atom I've added at the center of the bottom. And then I'm adding this one at the center of the front. And then I'm adding this one at the center at the top. Then I'm adding this one at the center on left. And this one at the center at the right. So there are 8 corners. And for each of those, 1/8 of the atom is in the cube. And then there are also 6 faces: the back, the bottom, the front, the top, the left, and the right. So 6 faces. And for each face, half of the atom is in the cell and half of it is outside the cell. So that's 8 times 1/8 is 1, plus 6 times 1/2 is 3. So there's 4 atoms in one unit cell for FCC. Okay? So here's my unit cell, 8 corners, 6 faces, and I want to know what is the relationship between the atomic radius and the lattice parameter A. So for FCC, the atoms that are actually in contact are the ones along this face. So if I were to just take that side plane and draw it in a view that's not exploded like this, not all separate from one another like this, that face actually looks like that. Well, that last one is a little, let's see if I can do that better. Here we go. So that would be the same as any of the faces on the crystal structure. So this is the face. And we know that the length of any side is equal to A. And so I've got 4 radii, 1, 2, 3, 4 across this diagonal. And that length is the square root of 2a. Right? So for FCC, for R is equal to the square root of 2a. Remember, for BCC, 4R was the square root of 3a. Okay, now I don't need this. I can go straight to the showing you the planes. Here are the planes that are activated, that slide past one another during permanent deformation. That plane is the 1, 1, 1 plane. Okay, and the direction of deformation is the 1, 1, 0, just the opposite of BCC. And like I said, I'll just go through that with the dry erase board. I think it'll come out a lot better. All right, so we did that. I'm going to use this to talk about our last topic here. So for BCC, there are 2 atoms per cell. So if I wanted to find the density of BCC, I could take the mass of 2 atoms divided by the volume of the cell, which is equal to A cubed. And for BCC, A is equal to 4R over the square root of 3. So the density of a BCC metal would be equal to 2 times atomic mass which is in grams per mole. And then I need the mass of 2 atoms, not 2 moles, so I'm going to need Avogadro's number. A mole is 6.02 times 10 to the 23rd atoms. That's Avogadro's number. So that's the mass of a unit cell. And the volume of a unit cell is A cubed, so that would be 4 times the atomic radius over the square root of 3 cubed. Now, an atomic radius is typically in what are called picometers, which is 10 to the negative 12 meters. So if this is picometers, and then I know that typically density is going to be in mass per cubic centimeter. So I've got 10 to the 12 picometers in a meter, and I've got 10 squared centimeters per meter. So that will convert my value into cubic centimeters instead of cubic picometers. And if I say I'm going to give atomic mass symbol, we'll call it M. And I got R. And I got Avogadro's number. I'm going to call that let's just leave it as Avogadro's number. Or I know that there's typically a letter symbol. There's so many different ones. We'll just leave it like it is. Density then is going to be equal to 2m times 3 square root of 3. That's the root 3 cubed. Divided by Avogadro's number. And then I've got r cubed. And then that 4 cubed is going to be 64. And then here in the denominator, I've got, this is going to end up being 10 to the 6 divided by 10 to the 36. So I've got 10 to the minus 30. So if I combine the Avogadro's power 10 to the 23rd and 10 to the minus 30, I have that density for BCC is equal to atomic mass divided by the radius cubed, given in picometers, times 6 root 3 over 64 times 10 to the 7 in grams per centimeter cubed. Okay, so let's try using that equation for an example. It says, okay, I have a hypothetical BCC material. There's my atomic radius. R is 150 picometers. And atomic mass is 10 grams per mole. This is a hypothetical, fictitious material, by the way. And I'm given, let's see, and then I'm giving that it's BCC. So if it's BCC, that means that A is equal to 4R over square root of 3. And it's asking me to calculate the density. We're calling it theoretical density because we're not measuring it, we're just calculating it based on what we know about how atoms are arranged in BCC. Okay, so density is going to be equal to atomic mass, which was 10 grams per mole, times, let's see, 1 mole is Avogadro's number, atoms. So now I have grams per atom, and this is BCC, and there's 2 atoms in one cell. So the moles cancel, the atoms cancel, and my numerator is in terms of grams, which is appropriate for density. Okay, the volume of that unit cell is A cubed. And I know that A is equal to, but we'll do it this way. We'll say root 3A is equal to 4R cubed. And then R is equal to 150 picometers cubed. And then we know there's 10 to the 12. Well, how about this? We'll just jump to, since we, rather than having to convert to meters and then back to centimeters, let's just say that there are 10 to the 10, there's 10 to the 10 picometers in 1 centimeter. And we'll cube that. So picometers cancel, and my numerator or denominator is now cubic centimeters. That's all good. And the A's cancel. Let's use another color so you can see. R's cancel. A's cancel. There's A cubed. Picometers cancel. Moles cancel. Atoms cancel. And so we have, for our density, 10 times 2 times 3 root 3. That's from the denominator in the denominator. And in the denominator here, I'm going to have 6.02 and 10 to the negative 7 and 150 cubed and 64, which is 4 cubed. So 4 cubed goes to the 64. This square root of 3 cubed is in the numerator now. The 150, make sure you remember to cube that. And 4 cubed is 64. That's my denominator. In the numerator, again, I have 10 and 2. And from here, from this root 3a cubed, I have 3 root 3. And that should be in grams per cubic centimeter. And you can take this 10 to the negative 7, move it into the numerator, and make it 10 to the positive 7. Okay? Now, I'm going to use the bottom of this page in a different color. To come up with the equivalent equation for FCC. So in FCC, there are 4 atoms per cell. And A is equal to 4R over the square root of 2. So density for FCC is going to be 4 for the 4 atoms per unit cell times atomic mass times 1 over Avogadro's number and that will give me a numerator that's in grams. All of that divided by 4R over square root of 2a, and this is a cubed. A cubed times 4 over square root of 2a cubed, and my R value cubed, and 10 to the minus 30. So this next example, I'm going to use FCC, and I'm not solving for density this time. I'm given density and crystal structure and radius, and I have to find atomic mass. So I know density is equal to, this is FCC, 4 times M divided by Avogadro's number and then I have a cubed and 4R over root 2a cubed. So what do I got here? In this case, I'm going to have 4 atomic mass. Oh, I see. That's right. That's what I'm solving for. So let's rearrange this equation. I'm going to say that M is equal to 6.02 4R over root 2 cubed divided by, times density divided by 4. Yep, and then I need to convert those picometers to centimeters. So I'm going to have 10 to the 10 picometers per centimeter cubed. So for this example, atomic mass, and it should end up with grams per mole, is equal to 6.02 times 10 to the 23rd atoms per mole. And then I've got in my denominator 4 atoms per cell. All right, so that's good. And I've got, this is FCC, 4 atoms per cell. Hold on. I just did that twice. I already have that in the denominator. So let's see, I'm going to have 4R is equal to square root of 2A cubed times A cubed times density given at 15 grams. Okay, you know what? I'm going to need to pause here. This is getting too messy. I've taken too many shortcuts in this equation. So let me back up, and I'll be right back. Okay, let's try this again. So we know that density is equal to the number of atoms per cell. So I'm going to call that X. X is the number of atoms per cell. So I've got atoms per cell here. I'm going to need to turn that into moles. So I divide by Avogadro's number. And then I multiply that by the atomic mass, m grams per mole. There's my numerator. Moles cancel, atoms cancel, and what I have in the top here is grams per cell. Then the volume is A cubed per cell. And I know that square root of 2, hold on, let me give that a variable so I can have a equation I can always use. We're going to say 4R is equal to YA, and we got to cube that, and Y is equal to square root of 2 for FCC and square root of 3 for BCC. Okay, and that R is in picometers. So then I need to take 10 to the 10 picometers per centimeter cubed. And my denominator now, the A's cancel, and I have basically centimeters cubed left. Okay. I'm going to keep with this. Am I? Yeah. So that's equal to X M times Y cubed divided by 6.02 R cubed, 64, and got 10 to the 23rd minus 10 to the 30th, 10 to the minus 7 in grams per centimeter cubed. So rho is equal to, well, I think it's time we can rearrange now, and it doesn't look too messy. So M is equal to rho times 6.02 times 64 times R cubed in picometers times 10 to the 7. All that divided by X, Y cubed. So I'm given a density, 15 grams per mole. 15 grams per mole times 6.02 times 64 and that 6.02 has with it atoms per mole. I'm going to want grams per mole. Okay, got it. That's 64. Okay, and then I've got R cubed. R is given as 125 picometers cubed, and then 10 to the 7 divided by, we're FCC, so this is X is as 4, And y cubed is square root of 2 cubed. Okay. And we'll do another example in class. And we know that this is all equal to density 15 grams per mole. Oh, shoot. No, it's not. That 15 is already in the equation. Sorry. We're solving for m. So density is grams, that's why. Grams per cubic centimeter. There we go. There we go. Now we'll end up with grams per mole. Because this is atoms here. Okay. So this was solving for atomic weight given crystal structure, density, and atomic radius. So first example, we were solving for density. Now we're solving for atomic weight. The next example is to solve for atomic radius if we're given mass, density, and crystal structure. Okay, so let's pretend we've got a material that has atomic mass of 25 grams per mole and a density of 8 grams per cubic centimeter. And we'll do a BCC crystal structure. And we're solving for R. Okay, so first, density is equal to the number of atoms in a cell, which is X, times the number of grams per mole, M, times 1 over Avogadro's number. So a mole is 6.02 times 10 to the 23rd atoms. And this X is in atoms. That's not in the denominator, it's in the numerator. So all of that gives me, in the numerator, X M times 1 over 6.02 times 10 to the 23rd. And the units, the moles cancel, the atoms cancel, and I have grams. And then our denominator, I've got A cubed is the volume of a cell, and Y times A is equal to 4R, and that's cubed. And R is my unknown. Okay, so R cubed is equal to X times M times, let's see, we're moving the R there, XM dividing by Avogadro's number. And then, let's see, we're going to have 64 left for that 4 cubed. And then in the numerator, I'm going to put Y cubed. So X is, this is BCC, so I've got 2 atoms. per cell. And then I've got M, the mass, 25 grams per mole. And I'm going down here, 6.02 times 10 to the 23rd atoms per mole. And then y cubed, let's see, this is BCC, so this is going to be square root of 3 cubed. Let's see, atoms cancel, moles cancel. So I have grams. Where's my density? Okay, I need to put that up here, density. So that is 8 grams per cubic centimeter. Oh, sorry. That density should go in the denominator. 8 grams per centimeter cubed. Okay, so let's see my grams. This is now in the denominator. My grams cancel. My moles cancel. My atoms cancel. The cell is self-evident. So I'm going to end up with 1 over 1 over cubic centimeters. So it'll be cubic centimeters in the numerator. And that should be it. So let's see. 2 times 25 times 3 root 3. And I should get, well, we'll go ahead and calculate our R in centimeters and then convert it. So divide by 6.02 times 10 to the 23rd and 8. And that's equal to R cubed in R in centimeters cubed. So we find that, and then you could convert that to picometers, which is the typical unit for R. All right. Okay, so that's the third kind of example of this type of problem with 4 possible unknowns. We've looked for density, we've looked for atomic mass. This one was looking for atomic radius, and the last is looking for crystal structure. Okay, so in this case, I really need to use known values for atomic mass and atomic radius. I'm going to pause this just a second so I can. Okay, with the other examples, I could use fictitious materials, but for this example, I have to have true values. So